Hey developers, welcome back to the channel. Are you tired of basic keyword searches that miss the actual meaning behind your queries? Today we're diving deep into the world of semantic search by combining OpenAI and BERT embeddings with vector databases using Python. Imagine searching for machine learning and getting results about artificial intelligence and neural networks, even though those exact words weren't in your query. That's the power we're unlocking today. By the end of this tutorial, you'll know how to build intelligent search systems, recommendation engines, and AI chat applications that understand context, not just keywords. We'll be hands-on with code throughout, so grab your favorite IDE and let's get started. First, let's understand what we're working with. Text embeddings are essentially high-dimensional numerical representations of text that capture semantic meaning. Think of them as coordinates in a multidimensional space where similar concepts cluster together. For example, words like king and queen would be close to each other, while king and banana would be far apart. These vectors typically have hundreds or thousands of dimensions, way more than we can visualize. Now, a vector database is specifically designed to store these high-dimensional vectors and perform lightning-fast similarity searches. Unlike traditional databases that use exact matches, vector databases use mathematical operations like cosine similarity to find related content. Traditional search: find documents containing machine learning. Literal match required. Vector search: find documents similar to the concept of machine learning. Semantic understanding. Here's our complete workflow that we'll build step by step. Step 1. Take raw text and generate embeddings using either OpenAI's API or open-source BERT models. Step 2. Store these vectors along with metadata in a vector database like Pinecone or Milvus. Step 3. When a user queries, convert their question into an embedding using the same model. Step 4. Search the vector database for similar embeddings and return the most relevant results ranked by similarity score. This pattern powers everything from Netflix recommendations to ChatGPT's memory systems. It's the backbone of modern AI applications. Let's get our environment ready. You'll need Python 3.8 or higher, and we'll install a few key libraries. For our core setup, we need Pinecone client, Pinecone-SDK, OpenAI client, OpenAI hashcode, GT-KN, sentence transformers, and FaceIL-SI. If you prefer other vector databases, you can use Milvus, PyMilvus, and Weaviate client, Weaviate client. You'll also need API keys for OpenAI and your chosen vector database. I'll show you how to set these up securely using environment variables. Now for the fun part, let's generate some embeddings. I'll show you two approaches, using OpenAI's API and using open-source BERT models. OpenAI approach. First, let's use OpenAI's embedding API. Notice we're using the latest text embedding 3 small model. It's faster and more efficient than the older ADA 002 model. BERT approach. Now let's see the open-source alternative using sentence transformers. The BERT model gives us 384 dimensions compared to OpenAI's 1536. Both work great, but OpenAI often provides slightly better semantic understanding. Now let's set up our vector database. I'm using Pinecone for this demo because it's cloud-managed and easy to get started with. Pinecone setup. The dimension parameter is crucial. It must match your embedding size exactly. Cosine similarity works best for text embeddings. Storing data. Now comes the magic moment. Let's implement semantic search. Watch how it finds relevant documents, even without exact keyword matches. Query processing. Look at this. When I search for "How does AI help doctors?" it finds our healthcare document with a high similarity score, even though the query doesn't contain the exact words healthcare or diagnostic tools. Advanced search features. Let's understand what these similarity scores mean. Cosine similarity ranges from -1 to 1, where 1 means identical and 0 means completely unrelated. Here are some crucial best practices. Number 1. Always use the same embedding model for both storage and search. Mixing models will give poor results. Number 2. Cosine similarity works best for text, but consider Euclidean distance for other data types like images. Number 3. Include rich metadata. It's invaluable for filtering and explaining results to users. Number 4. Monitor your similarity thresholds. Scores below 0.7 might indicate poor matches. When you're ready for production, here are key optimization strategies. Batch processing. Hybrid search implementation. Let me share the most common issues I see and how to fix them. Dimension mismatch error. Poor search results. While we used Pinecone today, let me quickly show you other popular options. Milvus, open source. Face, local. Each has trade-offs. Pinecone is managed but costs money. Milvus is powerful but needs setup. Face is local but limited in features. Congratulations! You've just built a complete semantic search system that can power intelligent applications. You now know how to generate embeddings with both OpenAI and BERT, store them efficiently in vector databases, and perform lightning-fast semantic searches. Drop your questions in the comments below. I read every single one and love helping you solve real problems. If this tutorial helped you, smash that like button and share it with fellow developers. Until next time, keep building amazing AI applications.